Lab Guy here. First, before we start today's video, I would like to thank my 5 new subscribers that signed up in the last few days. Welcome. I hope you enjoyed the channel and come back often. Good news to report. I have scanning circuits working for the Chief in both horizontal and vertical. They're not very good scanning circuits as test equipment goes, but they will be good enough to get the picture out of these antique tubes. As you know, I have 2 of these. This is the 2F21 Indian head test pattern monoscope tube made by RCA in 1939. This particular tube is probably made in the 1950s. They're very old, they're very interesting, they're valuable to certain collectors, but I think it's more important that we should have them working. And I'm going to try to build something to make them work. I have 2 tubes in case this one is bad, or in case the other one is bad. Nothing says that both of them could be bad, but we'll find out. How else can we find out without taking a hammer to this poor thing? So without further ado, I'd like to jump in and show you the schematics of the horizontal scanning circuit first and explain how we got there. The circuit looks deceptively simple. Let me walk you through the components first, and then we'll discuss how they work. The first part of the scanning system, of course, is the horizontal deflection coil, which is represented by these 2 upright inductors here. The power supply comes in at the top. It's approximately 50 volts. It comes through a very small value resistor. It's a fraction of an ohm. It's 0.39 ohms. Its purpose is to generate a small voltage representation of the current running in the yoke, which I will tap off and send to a future safety circuit that is used to cut off high voltage in the event that the scanning stops or is defective in some other way that I can figure out how to measure. Coming on down, the primary operating element of the deflection system is this transistor called the horizontal output transistor, or HOT. It acts as a switch. If you're familiar with automotive ignition systems, this circuit is not that unfamiliar. This would be the primary coil of your ignition coil, and this would be the points or the electronic ignition internal transistor switch. This diode functions to clamp a high voltage spike that is generated in this inductor when the switch opens. It protects the transistor. It also causes this field to collapse very quickly. This capacitor, as I discussed in the last video, is to create a resonant circuit with the inductor that gives us the flyback time, which is over here on this timing diagram, which I will get to in a moment. The input to the transistor is transformer coupled. I'm using a high-speed pulse transformer with a turns ratio of 1:1. The function of this is to isolate the high voltage of 50 volts on this side and those high voltage spikes I mentioned in the event that any of these components malfunction. This will prevent that failure from going backwards into my digital integrated circuits and burning up the digital system. We don't want that to happen. Coming into the digital system is the horizontal drive pulse. This is a pulse that goes low for 10 microseconds every 63.5 microseconds. That's how long it takes your television to scan one line across the screen. It turned out that sending the horizontal drive pulse directly into this system didn't work exactly right. It did work, but the problem was there was some delay introduced by these reactive elements. They are a timing element. So what was happening is the pulse would fire and the scan would start a couple of microseconds late, meaning that if you were looking at your television, you would see the picture shifted to the right. We don't want the picture shifted to the right. We want it framed up horizontally within the window of the screen. So I added this timer, whose function is to move the edge of this pulse earlier. It's actually late. You see that this horizontal drive pulse falls and triggers this timer, which then waits this long before it falls. I've drawn several falling edges to indicate that we can adjust the length of time it takes for the timer to time out with this control here, which I've named phase set. When you turn the knob, the picture will appear to move back and forth on the screen. This timer's job is to take the 10% duty cycle pulse. It's low for 10% of the entire period, approximately, and convert it to a 50% duty cycle, where it's low for half the time and high for half the time. And that is what switches the transistor off and on. When the transistor is switched on in the middle of the line, this would represent the spot is at the center of the screen. We switch the transistor on, current flows up through the coil, and the scan ramp starts here in the middle, not on the ends with the sync pulses, in the middle at zero current. This represents positive current going up, negative current going down. This is the current in the yoke. So that when this pulse turns on, the yoke starts to build a magnetic field. When it reaches the side of the screen, it starts moving the dot, the spot on the screen. When it reaches the side of the screen, the sync pulse fires, trips the timer, which actually was tripped the line before, which then fires the square wave pulse shaper a little bit early, so that this circuit starts a little earlier, and the flyback time, which is the period of time it takes for the beam to go from this side of the screen back to that side of the screen, occurs within what is called the blanking interval while the beam is turned off, so that we don't see that in the picture. Then when that wave falls, just as it gets to the bottom, this pulse turns off again. It turns off, and you see there's still that delay, and the scan starts again. This time the yoke is running from the charge in the capacitor. Before, the current was going this way when the switch was on, and when the switch is off, driving it up again, which starts our beam scanning from this side. When it gets to the middle and the switch closes, if we've done our work correctly, then the current flows in the transistor and it picks it up and discharges the capacitor. This represents the capacitor charging, and then this represents the inductor charging from the power supply current, and the cycle repeats over and over. I always get cross-eyed and confused trying to describe this. That is essentially the horizontal scan circuit. Now, the neat thing I discovered was using the signal generator to drive just this circuit was that I needed a signal here of greater than 8 volts peak to peak, AC. It was swinging 4 volts positive and 4 volts negative. And that worked. These chips that I use run on 5 volts DC. Each output can switch between 2 states, low of 0 volts or high of 5 volts. But the chip conveniently provides us with its output in both phases. When one of them is high, the other one is low. So for half of the cycle, the voltage is 5 volts going this way. Then for the other half of the cycle, it's 5 volts going this way, and the 2 cycles combined give the transformer the impression of a 10 volt peak-to-peak signal. I thought of it, and my brain said, no, that won't work. But let's hook it up and find out. The resistor is here because this coil has virtually no resistance. I think I measured it at 1/10 of an ohm. So connecting it directly to the chip would burn the chip out. So using a potentiometer tacked in the circuit temporarily, I dialed it until I got very reliable operation at various power supply voltages. With underdrive, the circuit will run with a low DC power voltage, but as you turn it up, it begins to sputter and fail, and so you then have to increase the drive through the transformer. This resistor is 75 ohms and is performing the function of being small enough for the transistor or the transformer to see a high enough voltage to trigger the output transistor, and yet it is high enough that as an active signal, this chip is not failing from overload. I'm actually drawing about 1.8 times the rating of the outputs, but they're only on for 50% of the time, so they're operating at a power level of about 90%. So the chip is really close to the edge. I haven't tested this over temperature. It could just simply fail if the temperature goes up in the summer. I don't know yet. It's working for now. I have a fix in mind for it should it fail under that condition. I can put a pair of transistors out here to buffer that. So that is the entire horizontal drive circuit theory of operation. Let's move on to the vertical circuit now. This is almost the final schematic for the vertical scan circuit. It uses 3 transistors and was completely lifted from a television camera manual, sort of, and adapted to my needs. The camera was Blonder Tongue TC1 and TC2 Vidicon transistorized cameras from 1960. Maybe even in the late 50s, I don't know. But I went through every service manual that I have, looking at various vertical circuits, to find one that was reasonably simple and would be easy to copy. Some of the notable high points of this camera's circuits were that they were in an era of germanium transistors where the PNP transistor was king, and so the entire circuit is electrically upside down to what we do today. The power rail for the circuit is minus 20 volts. I want mine to run on 12 volts. The transistors, as I mentioned, were germanium transistors. We're going to use silicon transistors because they're just way better. Also, since I'm converting to plus 12 volts, it's easy enough to take a circuit like this that has a PNP, an NPN, and a PNP transistor, and to convert it simply by changing them to NPN transistors, turn all of the electrolytic capacitors around, and change the power rail voltage to a positive voltage. He says, as if it were that simple, but it's kind of that simple. So this was my version of it. I used the conventional 2N3904 general purpose NPN transistor its brother, the 2N3906 general purpose PNP transistor, and a TIP29A vanilla flavored power transistor capable of 30 watts. I'm driving a much larger deflection coil than you would find in a Vidicon television camera. However, once these circuits are tuned correctly, very little power is consumed from the power supply rail. In a television, the horizontal circuit consumes a vast amount of power because it also doubles as a switching power supply to run other sections of the television. But the deflection yoke itself takes very little power. So, on to the vertical circuit. Let me just very quickly go through this. It's not very complicated. We have a positive going vertical drive pulse, which I think is a millisecond wide every 16 milliseconds. That's 60 cycles. So at the end of every 1/60th of a second, there's a pulse that goes high for just a brief moment and low again. That pulse occurs here, not here. This is vertical drive not. It's upside down. This is an inverter which flips the pulse to the positive polarity, a limiting resistor to protect the input of this transistor, and when the pulse goes high, this is a switch, once again, and it takes this capacitor and pulls it down, and it begins to charge up this way through this 47 ohm resistor. That's a very small value resistor. It charges up like that. 1 millisecond, in fact. Then the switch turns off. The capacitor then proceeds to discharge through both of these resistors, the 47 and a 1200 ohm resistor. So it charges up super fast through the small capacitor and discharges slowly through the big resistor. This is an inverting amplifier which amplifies the voltage change at this point, which is very small because the voltage is being developed across the small resistor. So the transistor amplifies the small wave here, which I believe was running about 0.6 volts. It's very small. It comes down through here. They have a 10 ohm series resistor, probably because in the germanium days this would act as a buffer. It's a very small value. It's almost like it's not there, to protect the transistor from a surge current, probably during retrace. Then there's a 2700 ohm resistor, which is truly the collector load resistor. So we now have our ramp signal here. I don't know which way it's going, whether it's positive or negative. It doesn't matter. And a series variable resistor to set the level driving the output transistor. This output transistor is configured as a Class A amplifier. Current always flows through the transistor, and as the drive voltage goes through it, the transistor acts as a third resistor, if you will, in the circuit that either draws more current or less current, causing the voltage up here it's amplified and goes over the capacitor to the yoke, which is here. And the yoke returns to the emitter, which is a form of negative feedback. This has a tendency to linearize the sweep to some degree. The sweep of this isn't perfectly linear yet. I'm still playing with component values here for the linearity control. Linearity is how straight is our ramp. Right now it kind of does this. It's curved. It should be straight, but it's kind of curved. We're going to live with that for now because I want to get on with it. And then finally, on this side is a voltage divider which applies a DC current from the center point of this adjustable resistor, the centering control, through our deflection coil and through this resistor to ground. Now, initially these resistors were pretty large because the television camera deflection yoke is a much lighter load than the television deflection yoke that I'm using. So I decreased the value of these resistors by 10 times. This was a 270 and I changed it to a 27, and this was a 680 and I changed it to a 68 ohm resistor. I didn't have resistors rated high enough, so this is a temporary arrangement as this transistor is hot enough to cook on right now and will probably fail. I'm using a 1/4 watt resistor where I need a 2 watt resistor. But it's working, and I'm going to reduce them in half one more time in order to create even more current, which this transistor will handle easily, in order to get the deflection to full screen on the 5-inch CRT that I use for testing so that I can see my scanning and verify that I have way more drive than I need for the Chief when it is finally assembled. The Chief runs its electron beam at 1000 volts, and my Cyclops, which is my scan test setup, operates its beam at 6000 volts. The higher the voltage, the more current it takes to deflect it, the more current in the deflection yoke. So if I can deflect my 5-inch tube to 5 inches with a 6000 volt beam, I'm guaranteed to have more than enough scan drive for the Chief. And that's the vertical deflection circuit. Would you all like to see it in operation? I know I would. For those of you who follow my channel regularly, you'll recognize the Cyclops, a project that I built several years ago for the express purpose of testing deflection systems, such as we're doing here now. You are looking at the first live demonstration, or YouTube demonstration, shall I say, of my scanning circuit that will drive the Chief. So we are now generating both horizontal and vertical scanning using the antique television yoke and being driven from my sync generator on board with the scanning circuits. This was the goal I set out to achieve a couple of weeks ago in order to get this ready to put into the Chief. So as you can see, it is actually scanning, and it's not great. It's kind of got some saddle distortion, and the upper right corner is pulled up slightly, but before you get too excited, if you see which direction to the upper right that is pointing, that is where I keep all of my modern magnets stuck to my workbench post. So the magnetic field is so strong it's distorting the image on this. I have a feeling that in the Chief this may not be as severe or even exist at all. Now that big black spot in the middle, oh, we can't get any closer, is where I accidentally burned this tube when I first built the project and had forgotten to limit the beam current within the tube. So there we are scanning on the test bed, and over here we can look at the vertical waveform on the scope. The upper trace is the output of the ramp generator that I showed you, consisting of the first 2 transistors of the vertical scan circuit. The bottom trace is the current being measured by my Tektronix current probe. The amount of current in the wire is very low. It's running about plus and minus 40 or 50 milliamps right now, and the probe I've got was really designed to look at signals in the amps. I bought the wrong probe. So it's noisy. So ignore the noise on that bottom trace, and you can see that we are running a reasonably straight-ish kind of a ramp signal. And if we come back and look at the tube, you can see that it is indeed scanning good enough so that we can move on. The very next thing I will be building onto the board before I move it into the Chief's case and start putting the cabinet together for real is the high voltage, 1 transistor high voltage buffer circuit to generate a blanking pulse. I'm not sure you can see it. I tried to zoom in, but there are blanking retrace lines in that little raster. And a raster is a series of scanned lines. Here's a side view of the Cyclops in operation. This is the current probe measuring the vertical scan waveform current. And over here is the board. Let me give you a nice close-up look at the board. This over here is the sync generator and the digital logic. This section up here is the horizontal scan circuit. And this section down here is the vertical scan circuit. The sync generator consists, of course, of a crystal oscillator, some pulse shaping circuits, the integrated sync generator integrated circuit, and some general purpose inverters, because sometimes the pulse I need from here is in the wrong polarity. This empty socket is missing a timer that's not being used yet. That will be used to create pulses that are used in the video amplifier chain. And this is the double timer that was shown in the horizontal circuit. This is the phase control that I mentioned for positioning the horizontal scan in frame with the sync pulses. This is the pulse transformer for the horizontal. This is the horizontal output transistor. To be safe, I got one that was intended to be used in very large computer monitors. I think the thing could run an electric motor the size of a wash machine. I'm not sure. It's a beast. If I burn that out, I'm going to go into horticulture or some other trade. This is the TIP29 power transistor right here for the vertical scan. We have the vertical centering pot, the vertical linearity pot, and the vertical size pot. And that is the complete board. As you can see, it's not very large at all. It's compact, and the circuits lent themselves to beautifully organized layout. I'm very grateful for that. Let's take a look at the back side of the board too. Now we're looking at the back side. Again, here's the horizontal scan circuit in this section, the vertical scan circuit in this section. If you have really eagle eyes, you will see the occasional surface mount resistors and other surface mount components that I use whenever possible, because using surface mount I don't have to cut wires for those parts. The sync generator starts over here with the clock oscillator, pulse shaper, sync generator, inverting buffers, and the 2 dual timer chips so far. This area has been left open. The scan failure circuits will be in there. So that is the current update and progress report for this project. Thank you for watching. If you enjoy the video, don't forget to subscribe. If you know anyone who likes this kind of thing, be sure to point them at my videos. My goal is to build a project that no one else builds. You can search YouTube for various television and camera projects of the nature that I like, and you won't find very many. And if you really like my project, jump in there and try to copy it. Or if you think I'm doing a terrible job, jump in there and do a better job and show me. I like it. More is better, right? So until next time, Lab Guy out.